Today we shall be discussing something about power calculation, how to carry out power calculation of a main engine. So let us start off. It's really very simple. So let us see a simple term from physics. We know force. What is force? Force is, yes, pressure into the area. Pressure acting over the area is called force. And next is the work done. So what is work done? Work done is this force into the distance through which the body travels. And next we will see the power. So work is in joules and power is nothing but work done in unit time. We take it as 1 second. So unit time, and the unit is joules per second, which is actually watts. So this is basic physics, and we are interested in calculating the power, which is work done per unit time in watts. Now let us see what happens inside a diesel engine. This is a piston. There is a pressure acting from top. Where is the pressure coming from? Due to the fuel burning. Yes. And when the fuel burns, there is a pressure acting over the area of the piston, which pushes the piston down. So this pressure is acting over an area of, let us say, capital A. The piston is moving a distance, let us say a capital L. So pressure is acting over the area A and moving over the distance L. So now let us attempt to calculate the power. So this pressure, let us take the pressure as P. The pressure is P. Okay, so pressure is acting. So let us see what is the force. We just saw force. Force is the pressure into the area over which the pressure is acting. So this is the force. This force is pushing the piston down by this distance. So work done will be force into the distance moved, that is the L, which we can say as force is pressure into area into the distance moved, and power is work done per unit time. So this is the work done when the piston moves once from top to bottom and again from bottom to top, because from bottom to top it is not doing any work. The only work being done is when the piston is moving from top to bottom. So this is the work done when the piston moves once down and up. So if the piston moves n times up and down in 1 second, then this would be the power. The piston moving up and down n times in 1 second. So this n is actually the revolutions per second. The movement of the piston up and down only once. So the work done is this one and the power formula is this. Let us simplify pressure into the distance which it is traveling, which is called the stroke length, into area of the piston over which the pressure is acting, into the revolutions per second, watts. This is the formula for power. But if the engine is a 4-stroke engine, then we divide the revolutions per second by 2, because in a 4-stroke engine, every alternate revolution is a power stroke. So this said and done. This stroke length will be given to you in the numerical. The area will be given not directly, but in terms of the diameter of the piston. We will calculate the area from the diameter, and of course the revolutions per second will be given. Now problem is this pressure. How to find out the pressure which is acting on top of the piston. So let us see. This is a power card which we shall use to calculate the pressure. Let me write the formula on top. So power is equal to pressure into stroke length into area into revolutions per second. This is the formula. Now we have to find out this pressure which is acting in the cylinder. This is the nature of variation of the pressure inside the cylinder. See, this is the variation. This is the maximum pressure. This is the minimum pressure. You see, the pressure is varying in a very odd manner. So actually this is the mean pressure. We will have to find out the average pressure because it varies from a maximum to a minimum in a very odd manner. So how do we do that? We measure the area enclosed by this power diagram. Let us say this area is small a millimeter square, and then we take the length of the diagram. Let us say that that is L, small l millimeter, and the mean pressure would be expressed as the area under the curve A divided by small l into a constant called the spring constant. This will give the mean pressure in bar, but we need SI units. So we multiply this expression by a factor of 10 to the power of 5, which will give us the pressure in Newton per meter square. And once we get the mean pressure, we put the mean pressure in the main formula and we get the indicated power for a diesel engine. So this is how it is to be done. So let us now try a simple numerical so that it is all clear. Let us try a simple numerical. The area of our indicated diagram taken off one cylinder of a 6-cylinder 2-stroke large diesel engine is 450 millimeter square. That means that the area of the indicated diagram is 450 millimeter square and the length of the diagram is 72 millimeter. Spring scale is 1.5 bar per millimeter. And next we come, the diameter of the cylinder is given as 900 millimeter. We have to convert this into meters and then calculate the area of the piston. So I have calculated the area of the piston. Nothing, we convert this into meters. This is meters, and then apply the formula pi d square by 4, where d is this diameter. That is how we have got this area. 0.636 meter square. That's the area of the cylinder. The stroke length of the cylinder is 1800 millimeter. We convert it into meters, 1.8 meters. So, and the RPM is given as 105. We will have to convert it into revolutions per second. We divide it by 60. We get 1.75 revolutions per second. Next we have to calculate the mean pressure by this formula. The A is the area of the indicated diagram, L is the length of the indicated diagram, K is the spring scale or spring constant. We get this much bar, we have to convert it into Newton per meter square. We multiply it by a factor of 10 to the power 5. So this is the mean pressure which we have got. Now let's go to the main formula for power, indicated power. This is the formula. Mean pressure into stroke length into area into revolutions per second. Let us just place one by one. This is the mean pressure which we have calculated over here. This is the stroke length which is given in the numerical. This is the area of the piston which we have calculated. and this is the revolutions per second which we have calculated from the RPM. So from this total we get the indicated power as 18.782 into 10 to the power of 5 watts. Let us break up the 10 to the power of 5. So 10 to the power of 5 watts, we break it up 10 to the power 2 and 10 to the power 3. So 18.72 into 10 to the power 2 becomes 1878.2 into 10 to the power of 3 watts, and 10 to the power of 3 watts means kilowatts. So this indicated power is for 1 unit only, and the engine has 6 cylinders. So we multiply this by 6. So for 6 cylinders, the total indicated power would be 11269.0 kilowatts. So this is how we calculate the indicated power for an engine. This was for 1 unit, this was for all the 6 units, that is for the complete engine. So this is how we calculate the indicated power. Now let us move on to more powers in the system. Let us see a machine. Now every machine has got an input, every machine has got some losses, and after the losses there will be an output from the machine. So we can say that input minus losses is output, or efficiency of a machine can be expressed as output of the machine divided by the input of the machine. But if we want to express this in terms of percentage, then we have to multiply this side by 100. So this is what a simple machine is all about. Now let us go and find out some other machines. Let us go to the next screen. Now this is the main engine for which we have just calculated the indicated power. So the input to the main engine is the fuel burning, which is IP. IP means indicated power. The main engine will have losses, frictional losses, and after that the main engine will have an output, which is BP or SP, meaning brake power or shaft power. What will be the next machine in line? Yes, you are right, that's the shaft. Okay, before we go to that, let us see the mechanical efficiency of the main engine. Output by input. We just saw that the efficiency of any machine is output divided by input. So brake power by indicated power. The next machine in line is the propeller shaft. The input to the propeller shaft is nothing but the output from the main engine. So input to the propeller is brake power or shaft power. The shaft will have its losses, and after the losses, the output from the shaft is called the dP, which is nothing but delivered power. So what would be the efficiency of the shaft, which is also called as the transmission efficiency? Yes, output by input. Output is delivered power, input is brake power. What's the last machine? Not the last machine. The next machine is the propeller. What's the input to the propeller? That is the output from the shaft, which is the delivered power. The propeller will have its losses, and after the losses, the propeller will give an output, which is the TP or the thrust power. So the efficiency of a propeller can be expressed as output by input. Output is thrust power, input is delivered power. So here we have come across 3 machines: engine, shaft, and then the propeller. No, this is not the end. There is still one more machine left, which is the hull of the ship. Now we just saw that the propeller gives off a thrust. The propeller gives a thrust, which is thrust power. The reaction of that moves the ship forward. So the input to the hull, we can say, is the thrust power. Input to the hull is the thrust power. The hull will have its losses, frictional losses, residuary frictional losses. And after that, the final output of the hull is the EP or the effective power. This effective power is the one which pushes the ship forward at the speed which we measure by the GPS or speed over ground. So what would be the hull efficiency? Yes, output by input. Output is effective power, input is thrust power. So that's all about indicated power calculation and efficiency of the various machines, main engine, propeller shaft, propeller, and finally the hull. So I think that's all for today. Remaining we will see in the next class. Thank you.